Okay, so let's begin. So in the same sequence of lectures that we are having about you know the uses of sum of squares and designing algorithms for average case problems, we'll actually see yet another primitive. Now, on the face of it, this particular problem and the algorithms we're going to study for it are not directly related to average case notions. But you'll see why I'm still including this particular lecture in the average case section. In particular, I'll talk about instances that are really motivated from average case problems that come around here. Okay, good. So all right, so first things first, what's what's this whole problem about? So we're going to talk about this tensor decomposition problem today. So in particular, a tensor for us would be an object of the following form: vi, actually let's use the notation I'll use throughout: AI, tensor BI, tensor CI. Let's say, this is an object. So what kind of an object is this? Here, A1 up to, let's say, AR are, and similarly B1 up to BR, C1 up to CR are all vectors in, let's say, some D dimensions, okay? While, and, this object that I have here is, an object in R D by D by D. So I think of this object as indexed by 3 indices, each of which take a value between 1 and d. So for example, the t, let's say, what's fgh entry. So the entry at the triple indicated by f, g, and h, where each of these are integers in 1 through d, is simply given by sum over I of the fth entry of the first vector. Oh no, oh no, it's all fine. The gth entry of the second vector and the hth entry of the third vector. Okay, so just so that the notation is perfectly clear, that's what this tensor notation means. Of course, you should not be surprised at all, because we've been dealing with certain kind of tensors throughout this class. In particular, you all have looked at moment tensors of distributions, moment tensors of pseudo distributions, etc. for a long time. We are just studying this object in slightly more detail right now. Okay, now I guess one notion I need is rank of a tensor. So in particular, I'm looking at, so the example I looked at is a tensor of order 3. So order just means it's just the number of indices that are required to describe a single entry of the tensor. That's what we call order. Okay, so this, the tensor t that I have here, is a third order tensor in d dimensions. Okay, so just so that the notation slash terminology is clear, so we are looking at the d dimensional third order tensor. Good. Oh, and I guess while we are discussing basic terminology, each of these vectors, the positions are important. So, AI tensor, BI tensor, CI is not the same as BI tensor, AI tensor, CI, and, the other permutations I can generate. And so in order to identify these permutations, I might use the following kind of language. I would say, for example, the first vector in, let's say, one of the terms, I'll call it as the first mode of the tensor. Okay, so to describe, which particular position in this 3 possible positions that a vector can appear, I use the word mode. Okay, and by I mean papers on tensors, etc. that you might read, might use a terminology. So just so that it's clear, hopefully this should be enough, I think. Good. So once I have a tensor like this, I'm worried about the simple idea of a rank of a tensor. And what's the rank of a tensor? Well, it's the minimum number. So in particular, I guess one way to define it is, if I have a outer product of 3 vectors, okay, where A, B, and C, or AI, BI, CI are d-dimensional vectors, we'll call this a rank 1 tensor. Okay, that's definition. And then I'll say that, T is rank R if R is the minimum integer, so that T is a sum of at most R rank 1 tensors. Okay, good. So now you know what a rank of a tensor is. Um, some kind of tensors that are very familiar to you are second order tensors. So, second order tensors are equivalent to, matrices, of course. And so you can see that the notion of rank that I just defined for third order tensors is simply the generalization of the notion of rank that we already know for, matrices. Okay. So in particular, if you recall, a matrix M d by d is, has rank R if it can be written as a sum, let's say rank at most R, sum of, R rank 1 matrices. And, rank 1 matrices are simply, objects of the form AI, BI transposed. Now, this, we look at it as a D by D matrix. Formally, the object AI tensor BI is not the same as AI BI transpose, but of course, there is a isomorphism between, the outer product of any two vectors and the tensor product of two vectors. So we don't have to distinguish, between these two kind of operations too much because they're clearly equivalent. We have some natural isomorphism, which means that, it should not be a surprise that, the notion of rank that we just defined is a simple generalization of, rank of matrices. Okay, good. So now, given that I dived right into tensors and rank of a tensor, um, I should now go ahead and justify what I want to do with this. Okay, given that now you're aware of the basic terminology. So given, let's start from two tensors, right? So two tensors like us matrices. So one problem you can be, so here are like maybe a couple problems you might be interested in solving about matrices. Okay. So let's two important linear algebraic problems. Given a matrix M, okay, find its rank. Let me actually, ask another problem, which is given a matrix M of rank R, find an explicit rank 1 decomposition of M. So, you know, in the usual tradition of asking trivial questions, let me begin right away. What do you think is the complexity of these two problems? What do we know about algorithms for solving these two linear algebraic problems? Time to unmute yourself and tell me the trivial answers.
DQ.
Good. So it's you can spot an algorithms person from a complexity person by trying to see how they describe time complexity. I would have accepted the following answer for this question: polynomial in D. But as Praneeth has described, the time complexity of these two problems is d cubed. Although jokes apart, we need to worry a little bit about when we describe time complexities, as we saw in the very first class, we have to worry about numerical issues here, right? Like the entries are supposed, I'm describing them as like entries over the reals, but of course when I give an input to a computer, the entries are going to be rational numbers, and then I have to care about what's the description of each of the rational numbers that appears, in particular the numerator and denominator of each of the rational numbers. And then I have to ask what is the dependence on the size, the bits, number of bits required to describe the numbers. But it turns out that there is a polynomial time algorithm for these two problems. Can somebody shout out the name of this famous algorithm? Okay, it's kind of hard to describe, I guess, whether it's the name
We
of the
can do
algorithm
Gaussian
or maybe the
elimination, I
process.
guess.
Say it again.
Gaussian elimination.
Gaussian elimination is a perfectly great name, yes, and some numerically stable version of it is precisely what you want to run here. I guess we've discussed the complexity of Gaussian elimination in some detail in the previous lectures. Another relevant primitive that you might be aware of is this algorithm for computing the singular value decomposition of a matrix. And that's in particular can be used to compute its rank. It can also be compute. It can in fact not just compute its rank. It can give you the minimum rank decomposition of a matrix. Okay. So with that discussion out of the way, here is something we can conclude for posterity's sake. Both 1 and 2, sorry Praneeth, are polynomial time solvable. Okay. And now given again another tradition of this class where we do not spend too much time on the motivations, applications, etc. I wouldn't do that today either. But this particular fact is extremely important to anyone who has ever spoken with somebody who does machine learning, or to anyone who has ever spoken with a friend of someone who does machine learning, or I could go on. You probably have heard about all these words: singular value decomposition, rank decomposition, etc. And there's a good reason for it. These two, this in fact, like, there are only really one primitive here. It's one of the most important, even if simple, algorithmic primitives in algorithmic linear algebra, and has like many applications. Okay. So let me not even go into any of it. Okay, because that's tradition. So let me just mention extremely important primitives in linear algebra. Algorithmic, numerical, whatever, linear algebra. Let's say that. Very good. Okay, very good. While we are at that, let me ask another trivial question, and let me maybe state it as an observation, which I will write after you tell me the answer. So, given a matrix of rank R, let's say, okay. So maybe question. Suppose M is a matrix of rank R, meaning there are vectors AIs and BIs in D dimensions, R of them, or R pairs of them, such that M equals the sum of the outer products of AI and BI. Okay? Can you calculate AIs and BIs? Who can spot the trick in my question and who can answer it?
It's not unique, right?
Exactly. We just discussed that there is an algorithm for computing a rank 1 decomposition, but there is no the rank 1 decomposition of a matrix. A matrix has many, in fact, infinitely many, decompositions, as long as its rank is at least 2. A rank 1 decomposition fortunately has a single decomposition, but that's also not interesting. As long as a matrix has rank at least 2, it has infinitely many decompositions. So there is really no way to calculate the components of some favorite rank decomposition of yours. Now, why is this an issue? You've all studied linear algebra. Why should we even be concerned about this? It turns out that again, if you are doing machine learning, or actually the real application where this kind of a observation was first discovered happens to be, believe it or not, psychometrics. Sounds like a made up word if you have not heard this before, but this is basically quantitative side of psychology, where in early 1900s, people were interested in measuring intelligence. Okay, like trying to understand quantitative measures of intelligence of human beings, etc. Again, I don't want to go into too much detail, but there is like a famous psychologist, Charles Spearman, who tried to do this. And the reason I'm talking about psychometrics and not sum of squares is because the way Charles Spearman wanted to solve this problem is that he basically so how would you even do this, right? You're going to take a bunch of human beings and ask them to solve some test, right? And you could call it an IQ test, whatever. You're going to make them solve some tests. You're going to receive some scores. Maybe you'll make each person solve multiple kinds of tests. Okay, GRE, Misha. And and you get the scores of these tests, and maybe you would want to look at the scores and compute some intrinsic quality measure of these human beings. You might want to compute, how intelligent they are based on their GRE scores. We of course already know this is such a futile attempt, but we could do that. And Charles Spearman wanted to do that. Okay. And actually, Charles Spearman wanted to go further. Okay. He wanted to not just measure some notions of intelligence. He wanted to claim that there are like only two kinds of intelligence, and he had some clever names for it, which I don't remember. Anyway, what's the point of this rant? Well, the way he set up the quantitative, approach to solve this problem is, he measured some tests, and it turns out that by some transformations, he actually was able to, phrase the problem of identifying the types of intelligence as, computing the rank of a certain matrix. Okay. And in certain, so he did his experiment, he constructed his matrix that comes from like some psychological theory, whatever. And, and he measured the rank, and it turns out that it's like close to rank 2. And, that was used as some kind of an evidence that indeed there are only two types of intelligence. Okay, psychology apart, let's say that you are Charles Spearman and you verified that you have a rank 2 matrix or whatever, close to a rank 2 matrix. And therefore you take it as an evidence that there are only two types of intelligence. But you also want to go ahead and measure these two kinds of intelligence. I want to find out how SOS intelligent you are. Even if you are very, very intelligent in, I don't know, something else, I care about, let's say, your SOS intelligence. And, how do I calculate that? Well, that's the problem of taking a matrix and decomposing the rank, getting a rank decomposition of it. But you are now in trouble. There are many, many rank decompositions of the same matrix. So it's not clear if at all you can identify these measures of intelligence or whatever, right? Okay. Doesn't matter whether you understand my psychometric psychobabble. The important thing is that these AIs and BIs might encode some hidden truth that you're trying to measure about the universe. Okay. It could be something in psychology, but it could also be something in physics or whatever, right? And being unable to compute some favorite rank decomposition might amount to saying that I cannot identify, the true parameters that I'm interested in. Okay. So for whatever reasons, you might actually be interested in computing some favorite, rank decomposition or whatever, and you will fail if that's all you've got. Okay. So good. So Charles Spearman started this, and actually psychologists eventually, even I don't exactly remember if they were the first one to use, but they certainly also used tensor decomposition, the primitive that we're going to use today. And the main observation behind that, oh, I guess I should write this other observation that Pranit already made. Rank decompositions are not unique. Let's say in general, because we are still in somewhat informal phase of our today's lecture, so that's what I'll use. But also an observation, it turns out that tensor decompositions are unique under mild conditions. So tensor decompositions for order bigger than or equal to 3, because order less than or equal to 2 is basically the case of matrices, are unique under some mild conditions. Okay. So in principle, if you could somehow, make a tensor out of this intelligence testing or whatever, then you could have just, tried to decompose the third order tensor instead. And then, you've gotten like measures of intelligence or whatever. In general, you could have discovered the truth, because you in general can hope to find unique decompositions into rank 1, into some of rank 1 terms of a, rank R tensor. Good. We'll study all of these, claims in more detail, and we'll study the formal versions. But that's actually the main reason that we are, discussing this today. Like the main algorithmic question we will discuss today is, why is this claim true? And, how can you make it algorithmically happen? Because just being true is not enough. We've got to have efficient algorithms to actually do this task for us. Okay. And of course, sum of squares will come in at that point. Good. Very good. Okay, I guess that's my motivation. That's all. Somewhat longer than usual lectures, but that's all I have to say why you might care about it. We'll actually, study these facts in more detail, so this motivation also will become clearer. Good. So Now we can identify the concrete problem before us. Given a rank R tensor, okay, find, A1 through AR, B1 through BR, C1 through CR. Okay. Oh, I should have said, by analogy with matrices, you should not be surprised that I will call a tensor symmetric or tensor decomposition symmetric if AI equals BI equals CI. Okay. Again, you should not be surprised that that this can be like that. You should not be surprised at this terminology, I guess. Good. Um, okay. So let's start our investigation into this problem, and we'll make it more and more formal and more concrete as we go on. Let's start our investigation of this problem by first, going back to the case of matrices and identifying at least some special cases under which the decomposition is unique. Okay. So let's ask the question, given a matrix M, let's say M is symmetric, okay? This will simplify notation and some extra work I have to do in many of the cases. So in fact, I will also look at only symmetric tensors today. Let's start by looking at symmetric matrices, okay? Let's say the matrix M has rank R. Can someone tell me some, and R is bigger than 1. Can someone tell me some, example of a condition under which M has a unique decomposition? What kind of decomposition might you look for in M that might guarantee uniqueness?
Eigenvectors are orthogonal.
Eigenvectors are, well, symmetric matrix has orthogonal eigenvectors. So what do you mean?
Distinct eigenvalues.
Good. So Praneeth has identified my punchline already. And here's the observation Praneeth is making. So suppose I don't just look for any decomposition. Okay. I look for, let's say I look for, let's say the only, I care about a special kind of rank 1 decomposition, namely eigenvalue decomposition. Right? So this is a special kind of decomposition. Because it's a restricted kind of decomposition, I can ask, well, are EVDs unique? Are eigenvalue decompositions for a matrix unique? So Praneeth already answered this question, but let's ask it separately anyway. Is an eigenvalue decomposition of a matrix unique? Does a matrix have multiple eigenvalue decompositions? And so this is, of course, a question to all minus Praneeth. So go for it. Break the symmetry.
If you have repeated eigenvalues, then it doesn't have to be unique.
Exactly. And so Tai is observing the following point, which is that if if the matrix has a eigenspace of dimension bigger than 1, then any orthogonal basis for that subspace would be eigenvectors. And because the set of eigenvectors is not unique, the eigenvalue decomposition won't be unique. Okay. Seen in a different way, an eigenvalue decomposition is unique only when the eigenvalues of the matrix are all distinct. Agree? Okay, so in fact, let me make this. Oh, I guess before going on, another observation. I guess today is a lecture of observations. So, what about computational complexity? Given a matrix, a symmetric matrix, can I compute its eigenvalue decomposition in polynomial time?
There's some numerical issues, right?
That actually exists for every question I'm asking today.
Oh, so then yes,
But Tim
polynomial.
is absolutely right. Actually, computing an eigenvalue decomposition of a matrix is actually a very non-trivial problem, which actually was solved in full generality only a few months ago, maybe less than a year ago. And so this is it was a trick question, but the trick was of a different sort than before. Um, for symmetric matrices, however, it turns out that eigenvalue decomposition is somewhat easier to compute, and the algorithm for that was known for a while. In any case, the complexity of these problems, at least the complications in this algorithm design problems, come from numerical issues, and these are very hairy issues which we will comfortably ignore for today because that's not our interest. Okay, so we're going to
So
think for our purposes
how do these
eigenvalue.
algorithms look like? I mean, you can have a matrix of integer values and have an eigenvalue which is irrational, right? So how would the output?
Good.
I mean,
That's already a problem, and so even if you allow approximations, like you could ask for an arbitrarily good approximation, and you would, let's say, for example, an epsilon is some target accuracy, and you can ask, I want an EVD which is accurate, let's say in max entry-wise norm up to epsilon, and I would want to have an algorithm that runs in time poly in log 1 over epsilon.
okay,
That's a very legit goal.
yeah,
Even though the eigenvalues are irrational numbers, this is an achievable goal. There is nothing information theoretic that bars it or representation that bars it,
yeah,
but it's not an easy problem to solve in general.
okay.
Yes. I guess I'll post a link to this really, really cool paper that solved this problem a few months ago. I'll post it on Didro just to let you know how even basic things that we probably assume must be solved are not always solved. Cool. For our purposes, we're going to think of EVD as an efficiently doable task. We will not focus on the complexity of that problem itself. And we will think of it as a polynomial time solvable task. Okay, I don't even care about whether it is cubic time or not. Assuming that, here is an observation I can now make. Suppose M is a matrix of the following form: sum I, lambda I, AI transposed. Okay. And suppose in addition, I know that A1, AR, so this is rank R, are pairwise orthonormal, or I guess they're just, maybe the right English is to say they're orthonormal. And let's say that lambda I not equal to lambda j for all I not j. Suppose, M is a matrix, and here is one of the decompositions I really care about it. Okay. Then there's a polynomial time algorithm to compute arbitrarily good approximations to A1 up to AR. Also lambda 1 up to lambda R, but my interest is in components. So let me just say A1 through AR. Is this a surprising observation to any, given our context right now? Unmute yourself and ask a question if you think this observation is not clear. Because I want to, our discussion kind of implied this, but I'm just clarifying. Okay, very good. So we found like one sufficient condition when matrix decompositions are unique, right? Namely, when I look for a decomposition where the vectors where the vectors that appear in the rank 1 decomposition happen to be, let's say, orthogonal, and let's say the corresponding eigenvalues are all pairwise distinct. Okay, of course, again, to avoid numerical issues, you would need there to be a gap between lambda I minus, like lambda I minus lambda j would have to be somewhat large in order for algorithms to exist, but let's not worry about it. Okay, so when lambda when no pair of lambda I and lambda j are equal, then we can just compute the eigenvalue decomposition of M. The eigenvalue decomposition of M, is also a decomposition of the same sort. Because the eigenvalues are distinct, the eigenvectors are uniquely identifiable, which means that I will have the same set of vectors. Okay. Now, I guess this observation, or at least all the speech I gave about it, should not be convincing to you. Why not? I lied a little bit, and I want you to spot my lie. This observation here is a lie. Why is that? So I'm claiming I can't quite hope to compute A1 through AR or even arbitrarily good approximations to them. Why not?
You can rotate them.
No. Rotation is actually, thankfully, not a problem.
Are you talking about the lambdas are not sorted?
The lambda i's are all distinct. What do you mean they're not what?
Uh, okay, never mind.
Well, I guess I'm observing that, if you look at this expression m, then it is invariant under the following transformation. Send AIs to minus AIs. Then, because m is a homogeneous quadratic in AIs, clearly, if I flip signs, you can't quite notice the difference. So I can't quite say that I can compute A1 through AR. I can only compute them up to, the sign. Okay. I can only compute the direction parallel to AI. I can't quite compute, the sign of it. So I'm going to say up to, okay. One of the many trick questions I will ask. Okay, good. So, okay, that was, all about matrices. That's basically all I wanted to, refresh for you. Let's go to tensors now, okay? And I guess maybe, qualitatively, the main thing we want to take away from here is that even though we found a sufficient condition for when matrix decompositions are unique, namely, when you force all eigenvalues to be distinct, look for, orthogonal decompositions, then yes, such decompositions are indeed unique, but it seems like a very restricted case. In many applications, for whatever reason, you can't quite guarantee that the decomposition you're looking for satisfies this pairwise orthonormality. And so, you are in trouble here. Okay. This is not good enough for, let's say, psychometrics, whatever. Good. So we're gonna study tensor decomposition today. And we're gonna show how they are more general in terms of their unique identifiability, etc., etc., and then discuss algorithms for them. Before I go ahead and do that, though, I wanna maybe point out the following important considerations from algorithmic perspective. So one thing you would want to demand from algorithms, especially keeping an eye on applications that your machine learning friends might have, is that you would want your algorithms to be somewhat robust. Okay. So what do I mean by that? Well, this word robust is of course extremely overused and means different things in different contexts. But in particular, you would not want your algorithms to really strictly rely on the assumption that M is rank R, right? Because M may not be exactly rank R. There might be some noise or whatever that adds, right? So you would want your algorithms to be resilient to some natural notion of noise. Resilient. And this is true for matrix decompositions and eigenvalue decompositions as much as it is true for tensor decompositions. This is really a desiderata for linear algebraic algorithms in general. You would want some level of noise tolerance to be baked into your algorithms, because otherwise they're not going to be useful. Okay. So what kind of noise would you want to handle? Um, you know, in many cases, you would estimate these matrices by taking samples or whatever, right? So you'll be averaging things. If you average some independent samples, you are left with what is called as a sampling noise. Just because m the matrix you care about might be the expectation of a certain distribution, but you can only compute it from samples, so you would get something close to the expectation. So you would want to handle sampling noise. So that can be thought of as handle noise that's random and independent. So usually the sampling noises in many generic situations can be assumed to be random and independent. So, if I perturb every entry of the matrix by some independent, let's say, random noise, let's say some tiny amount of, tiny variance Gaussian, I should be able to still, make my algorithm work in some nice, graceful sense. Okay. More generally, I would like to be able to handle perturbation noise, which are bounded in some appropriate norms. What does that mean? Well, instead of giving a rank R matrix, let's say I only give you M prime, such that M prime is M plus E. E is an error matrix. And, some appropriate norm that you care about of E is bounded. Let's just say. So in general, these two, well, the first property certainly, and, if you are a little bit bolder, maybe the second property are, very reasonable things to ask of any algorithm you might want to design for linear algebraic problems. So it's good to keep in mind. I want to point out that, of course, we saw a third kind of robustness in the last lecture, which was, in a situation where you have samples and some samples can be arbitrarily corrupted, etc. And let's call that notion of noise outlier robustness. We will not focus too much on this kind of, noise resiliency today. Okay. Not our focus. Good. Okay. Now that I'm done with the spiel part, let's go do some math. So let's talk about algorithms for tensor decomposition. Okay. And when we look at these algorithms, of course, we will ask, whether they satisfy this nice noise resiliency property that we would like, them to have. So the algorithm I want to tell you, it's like a very simple algorithm, but it has a really cool idea that comes up in like many different, applications. And so it's a very it's even though it's a simple algorithm, it's a very a nice idea to know and understand. Okay. And this idea has a bonus, which that it has nothing to do with sum of squares. Even though we will import it and use it and derive many more consequences out of it, we will discuss this idea without any SOS reason for talking about it. Okay. So in particular, this observation I'm going to talk about is due to Yenrik. So there is some weird issue with attribution of these algorithms. Actually, it seems like Yenrik never really wrote it down, and actually there are different authors who attributed this algorithm to Yenrik, even though they wrote it down, and that's the only published source that people know of. Let's not worry about it. Let's just use the usual terminology for this particular algorithm, this method called Yenrik's algorithm. And I'll clarify the issue with citations in the right paper in another Diderot post so that you know where to look for. Okay. Actually, by now there are many lecture notes that you can read to study Yenrik's algorithm. Okay. So we'll study it in a special case when so we just saw that if you have a eigenvalue decomposition where the eigenvalues are repeated, as in like there's an eigenspace of multiple dimensions, then you can't quite hope to recover a decomposition uniquely, right? We will show that in the context of third order tensors, this is no longer an issue. Okay. So let A1 through AR be orthonormal, meaning AI are vectors of length 1, and AI AJ is 0 whenever I doesn't equal to j. Okay. So then, given access to this third order tensor, so notice that if you look at it as if I had a second order tensor, then it corresponds to the matrix where all eigenvalues are equal to 1. And so if I was given a second order tensor with the same components, I won't be able to uniquely recover AIs from them. Okay. But let's say AIs, you're given this third order tensor. There is a polynomial time algorithm to recover A1 through AR up to okay. Let's look at the proof of this. And in order to make you remember this idea, I'm going to give it a name. I'm not sure if like everybody uses this name, but I'm gonna talk about the idea of this algorithm by means of the following description. I'm going to call it the random contraction idea. Okay. What is this idea? So here's the main observation. It's a very simple observation. Okay. Let G be a standard Gaussian. Okay. And suppose I give you access to the following matrix. Okay, so this is a matrix where the components are AIs. Okay. And the rank 1 term AI transposed is scaled by the inner product of AI with this random Gaussian G that I picked. Okay. Suppose I gave you this M sub G. Then I want to claim, that you're done. Can someone describe to me in one line why I'm done?
Compute eigen decomposition of this LG.
Right. But why would I succeed? Why would I succeed in getting the AIs?
With high probability, they will be the eigenvalues AIG would be distinct.
Right. Absolutely. So can someone tell me what is the probability over the draw of a Gaussian that the numbers G.A1, G.A2, so on up to G.AR are distinct?
1.
Exactly. The measure of the space where they are equal actually is lower dimensional, so it's actually just 0. So this is a 0 probability event that two of the G.AIs happen to be equal. Of course, this is where numerical stability becomes important, because you don't just care about them being distinct. You care about a gap. So let's maybe talk about that for a little bit. Why talk about distinctness when it's not enough? So, what's the expectation of this random variable? I'll not be too detailed, but let's maybe discuss a little bit. What's the expectation of this random variable? Notice that this equals expectation G.AI minus G.AJ square. Okay, so this is the difference between two of the entries, right? And because it's the inner product of a Gaussian with a vector, the vector happens to be AI minus AJ. G.AI minus AJ is also a Gaussian, yeah? And what's the variance of this Gaussian? Well, it happens to be the square of the length of AI minus AJ. AI and AJ are orthonormal, which means that the length of AI minus AJ is square root 2, right? So this quantity is exactly 2. Okay. So now what have we proven? We've proven that the difference of any two entries is actually distributed as a Gaussian with variance 2. Okay. So the probability that any of the pair has, so what's, okay, let's maybe discuss this. Probability that G.AI minus AJ is smaller than, let's say, 1 over n square. Sorry, 1 over, yeah, let's call it dimension square. What's the probability of this event? So I guess technically I haven't really talked about this, so I can't quite assume this, but this happens to be a certain property of a Gaussian called as anti-concentration. And it just says the following, that if I have a Gaussian random variable H, then the chance that it takes a value at most delta times its standard deviation. So H is a scalar Gaussian, is at most delta. Okay. So here G.AI minus AJ is a Gaussian with variance 2. And I'm asking what's the chance that it takes a value which is at most 1 over d square. That's, at most, this is at most root 2 over d square. by applying this anti-concentration inequality. Yeah. Oh, maybe I should, make it somewhat smaller. Good. So now, I have R square such pairs, right? So what's the chance that, so this is a bad event, right? Like this is an event that says that the gap between I and J is somewhat small. What's the chance that, this bad event does not occur? It is 1 minus root 2 delta over D square. What's the chance that none of the R square bad events happen? Right? You agree? This is an application of the union bound. And so that's it, right? If I make delta somewhat tiny enough, and I use the fact that R is at most D, if I make delta tiny enough, then this is saying that, with some reasonable probability, all of these gaps are, somewhat lower bounded. They are like inverse polynomial. So you can hope for, some polynomial time algorithm with some ease. Okay. So did that convince you? Like, okay, this is not obviously part of my plan, but just wanted to argue that, there is some natural way to argue gap between, these eigenvalues here. Anyway, good. So you all agree that this is done. So the question is, can I get access to this matrix, right? So let's ask that trick question now. Can I compute M sub G given the tensor T? Or how can I compute M sub G given the tensor T? Okay, it is such a simple trick, but sometimes it can be confusing with the notation. So let's do it, okay? Let's first imagine that T happens to be rank 1. Okay, let's say suppose T is this tensor, A tensor to the 3. Okay, for some vector A. So then what is T? Well, T is indexed by 3 possible integers in 1 through D, right? Compute the following object. Let's say, M sub G is the following matrix whose, oh, I have used G now. So what should I use? STU. Okay, good. That seems fine. One downside of working with tensors is that you run out of the alphabet very quickly. So anyway, I'm going to use S comma T to denote STth entry of the matrix. And let me define it by, let's say, the following operation. So what did I do? I take the T comma ST, the STUth entry of the tensor T. Okay. And then for every pair ST, I basically am taking a vector, right? So notice that for every ST, TSTU is a slice of a tensor. It's actually a vector. Okay, so it's a vector. TST is a vector. So let's maybe denote it like this, which what people like to do. Have a little dot here to say that that index is varying. This is a vector in, RD, right? Since it's a vector, I can take its inner product with my Gaussian, which is the d-dimensional vector, right? That's what I did here. This is the inner product of TST dot with the random Gaussian G. Okay. For every ST, I take the inner product of TST with G to compute the STth entry of M sub G. Okay. What is TSTU GU, which by the way, I can compute just by given access to the entries of the tensor T, right? What is this? If T is A tensor to the 3, well, the STUth entry of capital T is simply AS, AT, AU, GU. Okay. And so that's the proof in gory detail that I've actually gotten A inner product G, AS, AT, right? So the STth entry of this matrix is simply A dot G times AS AT, which means that M sub G is A dot G AA transposed. All good? Satisfied? Good. Now, okay, the point is that this is the operation that I just defined here, this operation is a linear operation, right? If I add two tensors, right? Then, applying this operation to the added thing is same as applying it to the constituents and then adding, right? It's a linear operation. So I'll observe that this is a linear operation on tensor, which means if T is some AI tensor to the 3, then the following operation TST dot G equals some I've started writing coordinates in brackets because, subscript was taken. I hope you won't mind that. Right? That's exactly what we computed above by linearity. And in particular, M sub G in this case would equal AI transposed AI in a product G. Okay, so I did that proof in gory detail so that, the notation is not confusing to you, but I hopefully convinced you that I can actually compute this M sub G matrix, which we were very happy with, by actually, doing a simple linear operation on the tensor T. Stop me if there are any questions, but this linear operation, because I took inner product with one of the modes of the tensor with a random Gaussian, this is called random contraction of the tensor. Okay, so I randomly contracted one of the modes of the tensor to produce a D by D matrix. And the cool aspect of this was that even though, the tensor's so-called eigenvalues, the coefficients on these AIs were all the same, the matrix I obtain has actually distinct coefficients. And then I'm done. Is this all clear? Is this all perfectly okay? Good, very good. So you've seen, Yandex algorithm in this case. Actually, before we go ahead, I want to maybe brief, even, so this is not exactly directly relevant to us, but I want to mention that, you can actually extend Yandex algorithm to the case when components are not orthonormal, okay? So here is a lemma. And I would be loose in the same way in terms of ignoring numerical issues like I was in the previous lemma. Apologies for that. There's a polytime algorithm that takes input T, which looks like this, AI tensor to the 3. Actually, again, it works for, asymmetric tensors too, but this one would be easier to describe. So let's maybe look at that. Where the only thing I know is that A1 up to A sub R are linearly independent. So I don't quite know they're orthonormal. I just know that, they are linearly independent. Okay. So there's a polytime algorithm that takes input T and outputs A1 hat, AR hat, such that, the set, okay, so let's say such that there exists some permutation pi. Okay. R to R, such that A hat 1, A pi I, minimum of these two quantities is smaller than some epsilon. So, this is just my complicated way to write that, I have recovered AIs up to permutation and signs. It's like, I can't quite tell which AI was the first AI. I can't quite tell the sign of AI, but up to those two symmetries, I have recovered the set of vectors. Okay. And so let me describe this algorithm. So I actually described, a version of this algorithm when AI is orthonormal, but I want to observe that in fact, I can go beyond that. Okay. So what's the idea? The idea is to take two random contractions. Okay. This is a little bit reminiscent of, power of two choices, but well, not exactly. So let's say, you took two random Gaussians, G prime, and you computed M sub G prime, okay, where M sub G, remember, is the same object that we looked at earlier. We saw that we can compute it, right? Now, what's true about M sub G and M sub G prime? So this time, this is AIs are no longer eigenvectors of M sub G, right? So you can't quite try to do eigen decomposition of M sub G to recover AIs, right? It's just some rank one decomposition now because AIs are not orthonormal. Good. But you have two of those. Okay. And so the idea is to observe that if you have two matrices, which share the vectors that appear but have like different coefficients on them, then you can simultaneously diagonalize them. As in, you can actually recover AIs. If you have like MG and MG prime, which are, weighted combinations of the same rank one terms and the weights are distinct, then you can recover the rank one terms uniquely. And the idea is kind of simple, okay? Maybe I'll just like vaguely or quickly describe it. So what's the idea? Well, if you look at the matrix U, whose columns are AIs, A1 through AR, I guess. Let's in fact assume that R is N so that I don't use, that's the largest set of vectors that can be linearly independent. So let's say, R is the dimension, okay? Just so that I don't carry another piece of notation. Good. So then, M sub G can be written, then M sub G is U D, let's call DG, U transposed, where U is, so where D sub G is basically, this matrix where, AI dot G appears on the diagonal. Okay. Wait. Is that correct? Yeah, I think it's correct. Still with me? I'm just like writing M sub G in this form, okay? So M sub G is this matrix. M sub G prime is U D G prime, U transposed, okay? And in particular, if I, so because, because the vectors are linearly independent, M sub G is actually full rank. I can take its inverse. So if I compute this matrix, M sub G inverse of M sub G prime, then, by linear algebra, I get U transpose inverse D sub G inverse U inverse U DG U transposed. And now you see what happens. I get U transpose inverse. This is identity. I get DG inverse DG. Sorry, DG inverse DG prime U transposed. And the point is that this, so even though I started with something of U transpose form, I've ended up with some matrix U, which is U transpose really, but U inverse, so it's called U transpose U. Then I have U inverse D, some diagonal matrix time U, which is an eigenvalue decomposition. Because I have, conjugation by a matrix and its inverse on the two sides. And notice that the entries of DG inverse over DG prime is some, diagonal matrix. Okay. And in particular, the entries on the diagonal would be distinct, because what are the entries of DG inverse DG prime? It's the entries of this matrix are AIG over AIG prime, or the other way around. And now again, by a similar argument that we did earlier, these ratios will all be distinct for different i's, which means, I have a diagonal matrix with distinct eigenvalues. And so what I've ended up with is again an eigenvalue decomposition where the eigenvectors are the vectors I care about and eigenvalues are all distinct, which means I can recover, the columns of u from it. Cool. That's it. That's so again, I'm not carefully analyzing this algorithm here. In particular, you can imagine that if these vectors are, very, very close to being linear dependent, like, by a very tiny perturbation, let's say you could make the set of vectors linearly dependent, then, this algorithm should not work, right? You can imagine that I have to have some notion of how far I am from being linearly dependent. That would be important here. And there is a notion called as the condition number of the matrix, with the AIs on the rows or whatever that I have to deal with. And so the running time of this algorithm and the error guarantees of the algorithm would depend on the condition number of the vectors. But I wouldn't, go into those details, at least, for our purposes. But anyway, the point here is that at least if you have some well-conditioned vectors, let's say they're not, orthogonal to each other, but, they're not, close to being linearly dependent in some precise sense, then in fact, you have a polynomial time algorithm to, recover AIs. Okay. So this is pretty cool, right? Like, not only were we able to relax the distinct eigenvalues condition, we were also able to relax orthonormality. And so you can see that, under some very mild conditions compared to at least matrix decompositions, third order tensor decompositions are unique. And in fact, you can recover them as long as the number of components in the tensor are not more than the dimension. And can someone tell me, just to make sure that everybody is following, why can't I repeat these arguments or, why can't I do this why can't I somehow, do decompositions where the number of components exceeds the dimension? Oh, it's a trick question. It has a simple answer. So, feel free to unmute yourself and inform me of the answer.
Linear independence.
Sorry, what?
Linear independence.
Yeah, exactly. I cannot have more than d vectors which are linearly independent. I cannot have eigenvalue decompositions with d plus 1 eigenvalues and so on. So, this algorithm in particular, fails when the number of components in the tensor are, bigger than the dimension of the tensor. Okay. So actually, this is a good opportunity to discuss a definition. Okay. But actually, let's not make it that formal. This terminology. So, we call a tensor undercomplete if, R is at most dimension D. Okay. And if the number of components exceed the dimension, we call it overcomplete. Okay. And you can see why there is a reason to, really make this definition, make this terminology. It's because there is a marked difference, when R exceeds D. In particular, the simple algorithm that we just discussed will not work. Okay. But, you can still ask the question of overcomplete tensor decomposition. And, I'll at least point you to an extension of one algorithm that we'll do today that will actually solve this problem. Okay, so we'll not only be able to extend Jandrek's algorithm, to more general situations to handle more error, but we'll also be able to do overcomplete tensor decomposition today. Okay, good. And yeah, so far, no SOS has happened, so I've got to, do more, right? Good. So any questions before, we move on?
So
You can
is there
also
like a,
recover. Yeah, go ahead.
or sorry, you can go first.
We can also recover signs of the vectors AIs, right? And minus AI won't be valid.
Very good, actually. Good point. I guess after I have recovered a conjecture decomposition, I can try to do what? Wait, how do you, what's your plan? What's your plan, Praneeth?
So we have these eigenvalues too, right? AI, comma G. So from that we can decide what
That
sign.
is a good point. Yes, for tensor decompositions, I can actually recover the signs of AIs. That's a very good observation. Because I have the eigenvalues. So Pranit is observing that I have the. I mean, when I do eigenvalue decomposition, let's look at the orthogonal case at the very least, right? When I do the eigenvalue decomposition, I not only recover the components, I also recover the eigenvalues, and I know G. So if I test, then only one of AI hat or minus AI hat would satisfy G dot AI of the right sign, right?
Yeah.
Good. So let me upgrade my theorem. Where did I say? So really it's correct, the theorem, because I did not write up to permutation. But okay, I guess that's implicit in the way. Good, very good. More questions?
Yeah, so you're saying that the rank of a tensor of a g by g by g tensor can be more than g, right?
Yes. Actually,
So
yeah, I guess I did not explicitly say that, but it can be, yes.
so like what's the smallest that or like what's the best bound on it for any tensor for
Good.
g by g by g?
Hi, you are awesome, because I forgot to mention all these points. Guess I wrote it down in my notes somewhere, but it's like somewhere else now. Okay, good. So let's answer Thai's great question, because it's actually something important. So uh, tensors, like third order tensors, in d dimensions can have rank up to, actually, let's maybe make two claims, just because to describe the fun parts of this. Third order tensors in d dimensions have rank at most order d square. Who wants to tell me a proof of this? If I take an arbitrary tensor, I claim that it has rank at most O of d square. Why would that be true? Okay, let me give a hint, right? Suppose you take a tensor and you construct the following matrix. It looks like this. It has this dimension of size n, this dimension of size n square. So it's indexed by, sorry. See, I'm messing up my n's and d's. So, it's indexed on the rows by entries from 1 to d. On the columns, it's indexed by, pairs. Okay. And I can, so this is a mate, this is, what, so, and at ijk, I'll write the entry ijk, tijk. Okay. So I've constructed an n d by d square matrix, right? So this, actually, I should also inform you that one natural way to solve many of these problems about tensors is to construct matrices from them. And there are multiple ways to construct matrices from tensors. For third order tensor, really, there are maybe two distinct ways, two natural distinct ways. But when you go to higher order tensor, there are many, many different ways. All of these different ways of constructing matrices from tensors have a name. They are called as flattenings. Okay? Because in some sense, why is it a flattening? Well, in some sense, you're killing the distinction between two of the modes of the tensor, right? Like here, for example, I merged the last two modes of the tensor. I called them into one giant vector. So, I flattened the two modes. That's the terminology people use. So this is a matrix obtained by flattening the last two modes of the tensor. Okay, good. So if I take this matrix, what is the maximum rank it can have? As matrix rank.
D.
Right, exactly. Sorry, yeah, I mean, I'm asking trivial questions, but yeah, that's my style, right? So in particular, I can write this matrix as, let's say UI, let's call it capital VI transposed, right? Maybe there are some, coefficients too, doesn't matter. Actually, let's maybe just absorb the coefficients into UIs. So you all agree that I can write this matrix in this form. Sum of D terms, each of the term looks like UI VI transposed. UI is a D-dimensional vector. VI is a D by D, well, it's a D square dimensional vector, which I can interpret as a matrix, right? Because what I can do now is, think of this as a linear combination of, I can, so, okay, maybe separately describe it. So VI is a D, in this decomposition, I treated, the last two modes as a vector. So I got this form, right? But now I can take each of these vectors VI, treat them themselves as matrices, and they are D by D matrices. So what's the maximum rank they can have? Go on. D. Okay,
D.
good. Sorry. All right. So VI can have rank at most D, which means it also has a decomposition. Let's call it, okay, I'm running out of alphabets. Let's call it YI ZI transposed. Right? So now what do? I just merge, like I replace each of the VIs by this D rank decomposition. And so, the total number of terms I get is D squared now. Okay. So let me not, go too much into detail. Here is like maybe a proof sketch. Let's call it a proof sketch. But is it convincing that a rank of a third order D-dimensional tensor can at most be D square? Convinced? Okay, very good. So now the question is this a good upper bound? Okay. So that's point number one. Point number two, actually it turns out that it's a good upper bound. In particular, random tensors have rank omega D squared. I'm not totally sure if I know a simple proof of this claim which matches constants, but at least if you don't care about constant, then this is not so hard to prove. Okay. So not only, do tensors have rank D square, most tensors actually have rank D square. By random, I mean, take each entry of the tensor to be a random independent Gaussian. Okay, good. So this kind of answers Ty's question, right? Up to constants, at least, tensors can and do have rank up to D square. Okay. But Ty's question is important in more than one way, because I can ask, given a tensor, is there a polynomial time algorithm to calculate its rank? So because I asked you this question about matrices earlier, it's only fair that I ask you about tensors. What do you think? Again, feel free to unmute yourself and make these guesses. So what do you think about the complexity of the problem? Do you think the problem of given a tensor compute its rank, is it easy? Does it have a polynomial time algorithm? You are remarkably conservative in making the guesses. But it turns out that this problem is actually a whole lot of NP hard. It's like, it's NP hard in basically any way you want to ask it. Computing tensor rank is NP hard. Determining if a tensor has rank at least R is NP complete. In fact, many variants of this problem you can imagine are actually all NP hard. So much so that there is a paper of the following title: Most tensor problems are NP hard. This is literally the title of a paper. You can check it out. It's a pretty cool paper by Hilar and Lem. I think it's, I guess I forgot to put the year, but I think it's about, maybe it's not that old, maybe 08, if I remember correctly. Okay, so this problem is NP hard, and actually so are many variants of it. In fact, just to remind you, or just to like tell you like how cool the state of affairs or how disappointing the state of affairs is, even though we know that even though we know that random tensors have rank omega d squared, it's an open problem to construct construct an explicit tensor. Give By an explicit tensor I mean give me a tensor whose entries can be computed by a polynomial time algorithm that you described to me, and it should be a deterministic algorithm. So give me a polynomial time algorithm that outputs a tensor given the input the dimension d, okay, that has rank omega d squared. This is an open problem. We do not know how to construct an explicit tensor with large rank. And so anyway, like several cool questions, and there are various reasons to care about this. It turns out that constructing tensors with large rank is intimately related to proving circuit lower bounds. So yeah, there are many good reasons to care about tensor rank, which we are not focusing on today. Anyway, Tai, I hope I answered your question and then some.
Yeah, thank you.
Okay, good. So good. Okay, so now let's go beyond the stuff, and actually let's not even try to go beyond. Let's try to discuss where SOS even comes in. Okay, and that's maybe the second idea I want to get across today. The heart of SOS approach. So what's the SOS approach to tensor decomposition? Okay, and in particular, I'll show you how to do over-complete tensor decomposition. Today, and in particular, I'll go tell you how to go beyond this, linear independence assumption, etc. By the way, like one thing to notice in the context of this NP hardness discussion that we just had is that in a certain sense, this problem is a microcosm of what we've been doing throughout this class in a certain sense, right? In the very first lecture, we started with this, hard in whichever way you think about problem of, finding a solution to a system of polynomial inequalities or equalities, right? And we said, well, this problem is NP hard. Even many special cases of it are NP hard, and but we don't give it up. We try to find interesting instances which are easy, right? And so we try to find approximation algorithms. We try to find easy instances. And actually, we are kind of doing the same thing at a lower level for tensor decomposition. We know that in general, we can't quite compute the rank. So we certainly, cannot hope to compute rank decompositions of tensors. But we are trying to find out many different conditions under which, we can do this, right? So anyway, in some sense, it's somewhat, I guess I find it quite interesting that, even though the problem is NP hard, we are trying to find out, we are trying to somehow, map out the instances which are easy. And actually, we are quite happy with it because many interesting instances of the problem that we care about are actually, do happen to be easy. Good, very good. Okay, so what's the SOS approach to tensor decomposition? And so the key idea is, the relationship of this problem to a different problem, okay? Polynomial optimization. Actually, maybe even more explicitly, polynomial maximization over the unit sphere, so over the following set. The set of all vectors of length at most 1, okay? So you'll see that, one extremely fruitful way to look at tensor decomposition is to view it as a special case of the problem of finding maximizers of a polynomial over the sphere, okay? And actually, once we make this connection, all known sum of squares based algorithms for tensor decomposition really rely on this connection that, you can somehow simply maximize a certain polynomial and focus attention on trying to find out all maximizers of the polynomial. And if you actually succeed in doing that, then in fact, you would be able to find the components of the tensor, okay? So in order to make this connection absolutely clear, let's prove in a completely different way the uniqueness of decomposition of a tensor with pairwise orthonormal components. We already saw this, right? We already convinced ourselves that tensors, third order tensors with pairwise orthonormal components are of course, have a unique decomposition. In particular, we even give an algorithm for calculating it. But we'll now, do this completely differently by focusing on the problem of polynomial maximization, okay? So in particular, I will give you a separate new proof that third order tensors with pairwise orthonormal components have unique decomposition. Good, let's do that. Here's a lemma. It's a very simple lemma, but I'll write it out in full. So let A1 through AM, or let's continue using A1 through AR, vectors in RD, orthonormal. Okay, good. So now, I have to associate with the tensor a polynomial. What polynomial would I associate? No mystery about it. Consider the following polynomial Px. Okay. Now, this is a notation that I think we have used in the past, but let me clarify what this means, okay? This is going to be a homogeneous polynomial of degree 3 whose entries are given where basically I use Tijk to as a coefficient of the monomial xi, xj, xk. Okay. Notice one thing, okay, which in some sense we have to be aware of. Okay, the tensor has symmetries, right? So in particular, the monomial xi, xj, xk appears how many times? 6 times, I think, because the monomial xi, xj, xk appears as ijk, jik, ikj, and blah blah blah, right? And each of those entries of the tensor could be different because the tensor is specified. In particular, tensor could have all possible triples of different entries. Of course, for our tensor it may not have, but I'm saying that in this summation, the monomial xi, xj, xk appears 6 times. Okay, for ijk distinct, and then different number of times when ijk have collapses and so on. Anywho, I guess what matters is that this is a homogeneous polynomial of degree 3. Okay. And then what? So let consider the following set of maximizers of this polynomial. Over the unit sphere. Okay, so I take all z's such that the polynomial evaluated at z, okay, this is just p of z, is bigger than equal to p of x when x varies over the unit sphere. Okay, so this is the set of maximizers of this degree 3 polynomial over the unit sphere. This set is equal to A1 up to AR. Okay. So notice, okay, so this lemma has a very, very, very simple proof. Okay. But it's important to observe, this conceptual connection it's making. It's saying that, the components of the tensor are precisely the set of maximizers of the associated homogeneous degree 3 polynomials over the unit sphere. Okay. And in particular, if I wanted to compute the components, then I could try to just compute the set of maximizers of this associated degree 3 polynomial. Okay. So let's prove this lemma because the proof is really, really simple. Okay. So, okay, good. So AI are orthonormal, right? Let's assume, and you'll see eventually that it doesn't matter, that R is equal to D. Okay. So let's say, I have D vectors orthonormal. So then, A1 through AR are in fact a basis. okay, for all vectors in d dimensions, right? So let's write x as, sum alpha I ai. So any arbitrary vector x can be expanded, as a linear combination of this orthonormal basis a1 through ar, right? And if I knew that x square, the norm of x, is 1, then you would agree that this is same as saying that the sum of squares of alpha I is 1, right? Because ai's are orthonormal basis. Good. So now let's compute p of x. Okay, then p of x equals, well, it equals t dot x tensor to the 3, which equals sum ai tensor to the 3 x tensor to the 3. And actually, this is equal to aix to the power 3. Okay. Now, today I want to be a little bit more cognizant of such things. I mean, these tricks, eventually after this lecture, I would expect you to be doing it in your sleep. But just for now, let me make sure that you agree with me here. Okay, why is the inner product of ai tensor to the 3 with x tensor to the 3 equal to aix cubed? Okay, why is that true? Well, ai need 3 indices. Let's call it stu. So the STUth entry of this AI tensor to the 3 is AIS, AIT, AIU. It multiplies XS, XT, XU, and then I'm summing up over all STU. And you would agree that I can write this as AIS XS whole cubed, and that equals AIX cubed. So that's the proof. Good. So I have this cubic form here. I have like the sum of third powers of these linear forms ai dot x. That's what exactly pix is. And now, because I have this expansion of x in the orthonormal basis ai, I can compute x dot ai very easily. You can see it is actually exactly equal to alpha I. So this is same as alpha I cubed. Okay. And then I'm only going to observe the following fact, that this is at most max over alpha I sum alpha I square. So I wrote sum, I write this as sum I alpha I times alpha I square, and then I upper bound this copy of alpha I by max of over all of the alpha i's. That's what I did here. And then observe that this is exactly 1. So this is max over I of alpha I. Good. And now everything that I want follows from here. 1. What is P of AI? When I compute the polynomial P at any of the AIs, well, the max of alpha I is 1, right? Because x, the x I'm computing it has actually one of the coefficients 1, others are 0. So P of AI is 1 for all I. 2, max of P over the sphere is at most 1. And along with this observation, it means that it's exactly equal to 1. Why is that? Well, max of AI is at most 1, right? Because sum of alpha I square is in fact 1. And finally, if x doesn't belong to the set A1 through AR, then notice that, max over I of alpha I is strictly less than 1, which means that P of x is at most 1, which means that x cannot be a maximizer of P. Is this simple, trivial proof absolutely clear? Because I've established a correspondence between components of this tensor and the set of maximizers of the associated degree 3 polynomial, homogeneous degree 3 polynomial. Very good. So, given this connection, what can I do? So idea for using sum of squares for tensor decomposition, well, simply try to find out the maximizers of the polynomial P, right? Because that's what we've established now, right?
Vish, I have a question.
Yeah.
Yeah, your proof seems to be only working in the under complete case.
Yes.
And you are looking at overcomplete here. Right?
I'm not looking at overcomplete right now.
Okay.
You're right. Yeah. I'm not trying to do overcomplete. I know I'm literally repeating the same thing that we did earlier. You're absolutely right. I'm not doing anything overcomplete here. We'll get to it. Hopefully, eventually, almost surely. So, so that's the idea for the algorithm. We're just going to try to attempt to find the maximizers of P. Okay. Now you have seen this method at least twice, which means that you know the next step. I have a search problem to solve. If I want to use sum of squares for doing it, what should I do? Well, I should focus on not finding the solution, but on certifying true solutions or verifying true solutions. Let's call it purported solutions. Right? I mean, this is not a surprise, right? Like we want to solve the problem, we instead focus on certifying. So what's the natural test to do to check if I have a maximizer of P or not? So somebody claims, so somebody comes and says, hey, you know what, here's a Y. Or actually, let's make it X because that's our variable constraint. So somebody comes and says, hey, you know what, I have a maximizer of P. What should I do? Well, check if P of X is at least 1, because we know that's the maximum value of P, and check that this is indeed on the sphere. Right? Check that both those conditions hold, and then you're done, right? So that's the natural test. And so now what do I have to do? I have a test. And now, I have to prove completeness and soundness, right? Completeness means that all the solutions that are like should in fact pass the test, which they do, right? We've confirmed that if I plug in X equals A1 through AR for any, for any of the A1 through AR, then PX is in fact exactly equal to 1. So it satisfies the constraints, right? So the thing to prove is soundness, right? And what does soundness say? Soundness says that, if X passes the test, then it must be a true solution. Okay. And for us, the true solutions are A1 through A sub R. So now, you can see that in a certain sense, in the real world, at least, we already have a proof of whatever soundness could mean, right? We already proved here that if X is not equal to one of the A1 through ARs, then in fact, it cannot be a maximizer. I can take the contrapositive. If X maximizes, it must be one of the A1 through ARs. So, this real world proof that we did that, says that the maximizers of P are in direct correspondence with the components of the tensor, it, establishes that it at least establishes the real world soundness, non-SoS soundness of the same test, right? So I'll mention this. I'm making trivial points so far, okay, but I want you to follow this. But the question is, if I have to design an algorithm within SoS, then, I need, so remember those checklists of things we had? The checks should be polynomial inequalities. Well, they are. The conclusion of the soundness must be a polynomial inequality. And that's the part we are missing right now. I mean, then the third part is giving an SoS proof that the checks derive the conclusion of the soundness. We'll get to that. But even before that, we are in trouble. How do I phrase the conclusion of the soundness? How do I say that if X passes the test, then it must be a true solution? What's a polynomial inequality way to state this? Let's start with attempts. And, like the point of this exercise, by the way, is that, sometimes, guessing these right statements or like composing this right statement is not so straightforward. It requires, at least some momentary thought. So what's the natural way to phrase the soundness? I want to phrase the claim that if X passes the test, which means X satisfies these two polynomial inequalities, then it must be, one of the AIs. What's the way to phrase this? Go for it. There are no wrong answers. Okay, let me take one attempt and to show you the pitfalls of it at least, right? One way I could say, a natural way is to say that the product X minus AI, let's say the product of the norms, right? The only way this product of the polynomial, so this is a degree 2 polynomial inside each, right? Now I'm multiplying them out. I'm saying that the only way this product is 0 if X is at least X is equal to one of the AIs, right? So this definitely captures the soundness claim here. Yeah. But what's the degree of this polynomial equation? So this is a degree R equation. And so, okay, if I allow myself the use of degree R polynomials, then I can do it. But remember, R can be as large as the dimension D. And so, if I need to even, if even the phrasing of the conclusion of the soundness requires degree D polynomials, then then I'm not going to get like a, efficient algorithm at all. So this is not a good idea, not because, it doesn't work, but because it takes too much of a degree. So what else can I do?
I have a guess.
Yeah.
Like the sum of AI dot X must be 1 or -1.
Okay.
Does this work?
Well, first of all, you have to show me why it captures the idea we want in real world. Why is this only possible when X is one of the AIs? Why can't I get this to work when X is not one of the AIs?
You need a square there, I guess. Maybe.
Oh, because the square is just
The square is satisfied for every X with norm. Notice that this is just true for all X's. Because AIs are orthonormal. Right. So yeah, this gives you nothing. And actually, this also, this doesn't uniquely characterize AIs, as in, I don't think this is satisfied only at AIs. But there is some merit to this kind of an idea. And okay, I mean, I don't want to waste too much time in doing this guesswork, but this was just to show you that, this kind of stuff can be somewhat tricky at times. Oh, let's see, because Peter is not here. It's up to me to look at the chat.
Oh, no,
Jeff
sorry.
suggests, yeah, Jeff suggests fourth power, and that's an excellent point. In general, I can take higher powers. Suppose for some large even integer t, I write this, I say that this should be equal to 1. Let's see what it means, because I want to claim that this is in fact a good, or at least it's, it's a decent way to capture that X is one of the AIs. Okay, why is that? So suppose this happens, right? By the same computation that we did earlier. Well, I guess let's not do the computation. Well, okay, yeah. Yeah, by the same computation we did earlier, this is same as saying that alpha I to the t is 1 because x dot ai is simply alpha I, right? Now, there are, let's say, r terms here. It means that in real life, there is a alpha I, which must be at least 1 over r. Yeah? What does that mean? It means, in particular, that alpha I, the magnitude, should be at least, so this is like 2 to the, e to the minus ln r divided by t, right? And now, if I choose, if t is bigger than equal to ln r over, let's say, delta, wait, is that what I need? Yeah, I guess so. Yeah, okay. Then, then this implies that the magnitude of alpha I is at least e to the minus delta, which is like 1 minus delta, right? So seems like I've made some progress, right? I only had a degree r equation to capture this conclusion of the soundness, right? But at least now I have phrased it in a way which involves only degree log r polynomials, at least for some constant closeness. Okay, so this is the soundness claim I'll work with for a while, and then we'll switch over and see, how I can get I mean, if I work with this, if I work with this degree, then the best I can hope for is to get a quasi polynomial time algorithm, even to match the guarantees of Yenrik, which is ridiculous. But we'll do that for a second, okay? Because even that will yield us, better guarantees and more general algorithms. And then towards the end, I'll explain to you, why there is a different way to do it. And that way actually uses Yenrik itself within SOS. Good. So let's take a break, okay? Let's take a break for 10 minutes, just like usual. And we will resume at 6:44 and come back and talk about how this kind of a soundness can be useful in getting new algorithms. Let's maybe wait a minute or so. Is there any question that people who are here already have so far?
Okay, could I ask a question that I had?
Yes.
Which is, I don't know how to square the NP hardness of what we said with the randomized contraction algorithm for earlier. Like, why is that not just explicitly computing the rank decomposition?
Absolutely great question. In particular, we have proven that if the components of the tensor are linearly independent, then you can't possibly have NP hardness. That particular instance cannot be hard. As I said, indeed, what we are doing is identifying a broad class of easy instances for tensor rank. That's exactly what we are doing, right? And in a particular way, what we are proving is, like, in some sense, in these settings where the tensor decomposition is unique, it's somehow also easy to compute. It's not true in general. I think, I'm pretty sure you can construct families of tensor where, the decomposition is unique in a certain way, but you can't quite hope to compute it. But what we are, via this uniqueness property, we are, chipping away at the instances which are easy in a certain sense. Does that satisfy you a little bit?
Yeah. I somehow I had forgotten that we used linear independence in the proof.
Yeah, like in particular, if you have, let's say, more than the dimension number of components, then at least the proof that we've done so far will not work. Right. And in fact, it turns out, so I told you earlier that, there are omega d square rank tensors, but generically, we only know how to decompose tensors of rank smaller than d to the 1.5. And in general, like, there is no known algorithm for handling, basically any reasonable class of tensors which have rank bigger than d to the 1.5. So there's like a whole regime in between where, we think, all the NP-hard instances probably lie. Good. Yeah, like in some sense, we are playing at the edge of NP hardness, right? Like you have to keep walking without falling down. It's an interesting thing to do. All right, so let's continue. So we phrased, a type of soundness where, we were able to use polynomial inequalities to describe soundness. So now, the next item on our checklist is to give a sum of squares proof, that starts from the checks that we make in the test and derives the conclusion of the soundness, right? Let's do that. So actually, let's do a step one of that. This step one, I remember Jeff suggested, before we arrived at this particular version of soundness. So let's write down lemma. The lemma says that the inequality constraints in my checks. So, AIs would be orthonormal throughout, this few lemmas that I'm going to write. I'll relax them eventually, but right now they're orthonormal. So I will not repeat that hypothesis, okay? And with an eye for things that I want to go to later on, let's, not write bigger than or equal to 1, but bigger than or equal to 1 minus delta for some parameter delta, okay? So, the check we devised had a test, which tested like you're bigger than or equal to 1, but eventually, we'll have noise, etc. So let's, relax that test and check only bigger than or equal to 1 minus delta, okay? And think of delta as some tiny constant for now. So what do I want to say? So any x that satisfies the system of constraints, let's call the system of constraints A, script A, derives the soundness check, which is, let's, do some baby version of soundness first. So it derives the following inequality. AIX to the 4 is at least, let's say 1 minus 2 delta. For whatever reason, my notes doesn't have it. We'll see. Okay. So remember, our soundness basically phrases the same condition with a power t appearing here. Okay. Now, by the way, all of this should appear ridiculous to you. Okay. And if it's not, then something's wrong, because we already have an algorithm for the orthonormal case that works in polynomial time. And we are designing a quasi-polynomial algorithm that somehow, is trying to achieve the same guarantee. So it is somewhat ridiculous. But bear with me, okay? We will decrease the amount of ridiculousness very soon. We'll soon show that this way of thinking actually gives us more general and more powerful algorithms, okay? Good. So let's prove this though, okay? Let's prove this baby step first. So here's a very simple proof of this. And the proof is going to rely on the same kind of inequalities that, we've built the whole class on. So the main observation is, and you will tell me the reason for this inequality. So now that I've written the inequality, who wants to tell me 2 words that justify this statement?
Cauchy Schwarz.
Yeah, exact 2 words I was looking for. And because we gave a sum of squares proof for it, I can do the following. Oh, given that I've already used degree 6, I should do that. Okay, good. So you're all satisfied with this, and that's great. And now, because of orthonormality, so focus on each of the steps, okay, because we'll relax them very soon. Because of orthonormality, some AIX squared should equal what? Well, I'll claim that they should equal any issues with that? And I'm saying that, I can do this within sum of squares. Why can I do this? Well, because it's a polynomial identity. I'm using the identity sum I AI x square equals x square. This is a polynomial identity. It's literally like the two polynomials on the left and right hand sides are equal. I do not know what the AIs are, but this identity holds. A different way that you might, find this easier to digest is to look at the left hand side as X transpose some AI transposed X, and then note that some AI transposed is identity. So this is X transpose identity X, which equals the norm of X squared. And this is a equality of these two left and right hand sides as polynomials. So, it's simply a polynomial identity that I used. Okay, very good. And now A has the constraint that X squared is at most 1. So, this is at most I equals 1 through R, AI X to the 4. And now, I'm done because I observed that my constraints derive that sum I from 1 through R of AI X cubed is at least 1 minus delta. So, the left-hand side of this, after squaring, gives me that, it's at least 1 minus delta square is a lower bound on AI X to the 4. And I have a degree 6 proof of it. Okay. And now I'm just using that 1 minus delta square is at least 1 minus 2 delta. Okay, that's it. That's the proof. Good. So very good. So now, let's do the general version. Okay. So same business here. Actually, let me not even write it again. A derives in degree k plus 2 in variable x the inequality sum I from 1 through R AI X to the k plus 2 is at least 1 minus O of k delta. This is basically the analog of what we did for 4, like delta changed to 2 delta there. So I'm saying that, when I take k powers, I should have a loss of k delta. Well, yeah, that's that. Let's prove that. Okay. And the proof is kind of similar. Actually, the proof, let me write it as a standalone inequality. The proof uses the following inequality. Let V1, V R be scalars, okay? Then for all integers S, there is a degree S sum of squares proof, unconstrained degree S sum of squares proof that proves the following inequality. Vi to the 4 is at most I from 1 through R Vi square to the S sum I from 1 through R Vi to S. So what do I have here? Maybe a nicer way to interpret this inequality is to look at V1 through VR as coordinates of a vector. And then what I have here is the fourth norm of V raised to the power S is at most the L2 norm of V to the 2S times the 2SF norm of V raised to the 2S. Okay, so it's some comparison inequality between norms of the vector V. Okay. We'll prove this in a second. It doesn't have such a complicated proof. At least, I guess I'll not do the complete proof. I'll refer you to some other inequality modulo which it has a relatively simple proof. But let's, use it and see at least that it finishes the job, okay? So proof using lemma. I'm going to use the substitution rule that we learned in the calculus of sum of squares proof and substitute Vi equals AIX for all I. Okay. And now I have a degree 4 and I'll use it with S equals, what should I use it with? K over 2. So K is an even integer. I should have said it somewhere. Did I say it? Okay. So I'm going to invoke this inequality with S equals K over 2 and with substitution Vi equals AI dot X. Now what do I get? I get that sum I AI X to the 4 whole to the s is at most sum I ai x square to the s ai x to the, I should write this as k over 2s good. So I'm going to say I'm done now because I know that this is equal to x squared to the k over 2, that is x to the k, which is actually at most 1 from our constraints. And so what have I proven? I have proven, so I know that the constraints derive this in degree 2k or whatever, k plus 2. Wait, what did I do? Something is a bit off. Oh no, nothing is a bit off. My degree is a bit off. That's all that's happening. Let's call it 2k. Okay. So now I do have a, oh wait, do I have a 2k degree proof for this? Yes, I do. Good. In variable x, so this is after substitution, I have a 2k degree sum of squares proof in variable x of this inequality. Then I use the fact that this is at most 1, and so I have this inequality over here, and so now I really like the right hand side over here. The left hand side, so I wanted to lower bound the right hand side, right? That's what my goal was. And the left hand side is something that we already proved. So in this first version of the lemma that we proved here, we proved that the same constraints derive that sum ai x to the 4 is at least 1 minus 2 delta. So now if I use it, I get a lower bound of ai x to the k is at least 1 minus 2 delta to the k over 2. And now if I did it correctly, this is at least 1 minus k delta. So that's it, okay? And I guess it seems like I proved it for k and not k plus 2, so let's do that. And k bigger than 2. Wait, k bigger than 4, I suppose. Otherwise, this is not an interesting statement. Good. Still satisfied? Everything is okay? Modulo this proof of the vector inequality. So let's prove that, okay? So, okay, let's maybe, okay, whatever. So proof of lemma on vector norms. Okay, so how are we gonna do this? Well, the way I'm gonna do is look at my notes. We'll prove this. Okay, so what's the vector inequality we are looking at? We're looking at sum I vi to the 4 to the s is at most sum I vi square to the 2s, sum I vi to the 2s. Okay, so what we'll do is expand left and right hand sides. Okay, so if I expand, so this is a sum of r terms raised to the sth power. So you will agree that I can write it as v to the 4 alpha s choose alpha. So what is this expression? So s choose alpha is the so-called multinomial coefficient, which is simply s factorial or alpha 1 factorial and so on up to alpha r factorial. Okay, I'm just doing the multinomial expansion. And v to the 4 alpha means, so alpha is a vector, okay? It tells me what power, which coordinate was raised to what power. And so, I have all of them will be multiples of 4. So, I have 4 alpha here, and alpha ranges over, all possible subsets of, R of size S. So does it make sense? Like this is the multinomial expansion of the left-hand side, okay? And I'll do the same thing on the right-hand side. I have sum over all alpha. This time I have S choose alpha, but I have something raised to 2 alpha because I have a square sitting in there. and then I have vi to the 2s. Okay, so now I'm, so because I set it up both the sides as sum over all possible subsets of alpha, of size s, I can do a term by term comparison. Okay, the reason I can do a term, and by the way, like the reason term by term comparison is actually okay is because, all of the left and right hand sides are actually sum of squares, right? Like they're all raised to even powers. So, they're all sum of squares. So it's okay to do a term by term comparison. Okay, because then I can use the calculus of sum of squares proofs to add the SOS inequalities I derive. So let's look at the alpha th term, right? What's the alpha th term? Both of them have coefficients. S choose alpha on, both sides. So, enough to prove v to the 4 alpha is at most v to the 2 alpha times sum I vi to the 2s. Right? And actually, from here, it's also enough to prove that v to the 2 alpha is at most sum I vi to the 2s, because if I have this inequality, then I can just multiply by v to the 2 alpha on both sides. It's a square, so it's a legit thing to do, and I'll get the inequality I need. So my goal is now simply to verify this fact, right? So let's, make sure that we first of all believe that this fact is true in real life. Okay. What does v to the 2 alpha look like? So, this notation can be somewhat confusing. So let's take an example, right? Like v to the 2 alpha, for example, one example of v to the 2 alpha is is let's say v1 to the 6 v2 square. Okay, so I have taken like 6th power of first term, 2nd power of v2, right? And so this is a term for alpha equals 4, right? Like a set of size, a multi-set of size 4. If I took a multi-set of size 4 and raised it to 2nd power, this is what I will get. Okay, and I have to prove that this is at most, on the other side, I have to prove that this is at most some vi to the 8, right? That's an example of this. So what's the real world proof of this inequality? Oh, it seems like there are answers in the chat. I don't have my TA helping me out today, so I actually don't know what Muirhead's inequality is, Misha. But I'm going to use the good old AMGM inequality on this. That's all I'm going to do. In fact, I'll just prove that this is at most v1 to the 8 plus v2 to the 8, which is of course enough. And so why is this true? Well, okay, now that I've told you, can someone tell me the AMGM proof of AMGM based proof of this? Okay, so look at the following, 8 variable AMGM. I hope you will agree that A1 plus A8 over 8 to the 8 is at most, is at least, wait, maybe that's not what I want to do. Okay, let's actually go on with it anyway. This is certainly true, right? But I guess, can I actually?
Don't you need like the power mean version of AMGM?
I need a power. Yeah, you're right. Like I need this stricter version of AMGM. But actually, you can use AMGM to prove it.
Yeah.
So it's not such a non-trivial part. Okay, so if I apply it with A1 through A6 set to V1 and A7 and A8 set to V2, then I get that V1 to the 6 V2 square is at most whatever 6 over 8 V1 to the 8 sorry V1 plus 2 over 8 V2 to the 8. And now, as Misha said, I actually need to prove that this is at most V1 to the 8 plus V2 to the 8. Okay, so I'm going to be somewhat sketchy. Okay, so the way to prove it is to observe that when I expand it out, because I have a convex combination here, 6/8 and 2/8, I'm going to get like many terms, and the coefficients of all of these terms add up to at most 1. Okay, I actually don't see a proof. I just realized that there is an issue.
I think you can get 6/8 v1 to the 8th plus 2/8 v2 to the 8th.
You're saying this is true?
I think that one might be true.
Okay, looks true to me. Yeah, actually, it kind of looks true to me. But because I assumed that I would be able to do this proof on the fly, I did not write it down. And now that I cannot do this proof on the fly, it means that we'll have to move on and assume that I can do this proof on the fly somewhere, sometime. Okay, so let's forgive my transgression here of not learning to do this Muir head proof and assuming that I can just work it out. But basically, there is some appropriately clever version of AMGM, sequence of AMGM inequalities you can apply, and you can actually get this inequality, okay, to hold. Wait, is there a suggestion on the chat?
Oh, I was saying this is just Jensen.
Is it Jensen? That would save me it. Yeah, this is Jensen. Whoa, Tim, my friend, you've done it. So this is Jensen, indeed. Because I have a convex combination raised to some power, and I use the convexity of the 8th power function to conclude that this is at most this. Okay, good. So not so bad after all. We do have a proof of this inequality, and actually, the same thing. So this is maybe an example, but the same thing works for proving this inequality in general. The question is, why can I do it in SOS? And for the second step, I think you could work it out using Cauchy-Schwarz, which I will not do because I haven't written it down. The first step, you need a SOSization of the AMGM inequality. And for some fun exercise, can you guess the year in which this was proven? What year was the SOSization of the AMGM inequality proven? Actually, I don't remember the year. I remember the century. It's 19th century. So, yet another, example. So I gave you another, one example I gave the last time where, Lagrange's identity was proven by Lagrange for our algorithms about 100 years in advance. And same thing was done for, AMGM inequality. It was proven by this guy Hurwitz, about 100 years in advance of when we needed it. Actually, there's a simpler proof than Hurwitz. I actually don't know. Hurwitz really has this focus on giving a SOS proof of AMGM inequality, and I actually still don't understand why they were interested. I mean, I see strong motivations now, but Hurwitz saw it like 100 years ago. These people are so prescient. Anyway, there is actually a simpler proof that we know now, which actually can be done in 2 pages, but I will not do it. Okay, but maybe the thing to focus on is like how general purpose these tools are, right? Like we pick up these few basic inequalities, Cauchy-Schwarz, Hölder's we used the last time, almost triangle that we used, time before that. Today we are using this AMGM. We are using this Cauchy-Schwarz version of Jensen, etc. And we just like keep shuttling between these inequalities and we keep succeeding. Okay, that's the SOS story. Learn a few inequalities and use them to death. Good. With that informal, spiel, and not a mathematical proof, I'll stop with the proof of this inequality and claim that you can do it in SOS. I'll point you out to Hurwitz's proof, on Diderot again. But that's it. We have the inequality for vector norms. So we actually have a sum of squares proof of our soundness, which is this, I suppose. I should have called it by soundness. Okay, good. So, before moving on how, this actually is useful for algorithms, which we haven't at all studied it, let's, quickly observe what we really used in this whole proof, okay? To see, how much we can generalize it, okay? First is, where did we use orthonormality of AIs? In this proof, where did we use orthonormality of AIs? Let's go back to, this 4th power derivation, okay? There it is. In this part, where did I use that AIs were orthonormal? Well, only in, concluding that some AI x square is at most x square. I mean, it was equal to here, but if it was less than equal to, I wouldn't have minded, right? So all I needed was that some AI x squared should be at most, norm of x squared. In particular, if I had proven some weaker version like this, I wouldn't have minded either. I would lose I would lose some additional 1 minus epsilon. My accuracy will suffer. I will have 1 minus 2 delta minus 2 epsilon. Not such a big deal though, right? So in particular, the observation I'm making is that I didn't really strongly need orthonormality of AIs, which is great because that's what's going to allow us to, immediately go to overcomplete case. Okay, that's one. And the other thing I want to observe is that I didn't really need that the tensor itself, have no noise. So let's, quickly phrase a version of, the same soundness, which works in slightly more general situations. We'll not discuss a proof of that in detail because I want to tell you about the algorithm. So let's maybe talk about noise resilience generalization. Okay, so here's a lemma. Suppose actually, let me write it this way, and then I'll tell you, in fact, that even this is what I don't need. This means that the largest eigenvalue of the matrix of the sum of these AI transposed is at most 1 plus epsilon. Notice that if AIs are orthonormal, then in fact this matrix is simply identity, in which case the largest eigenvalue is 1. So I'm saying, let's say it's like somewhat relaxed in that. Suppose it is at most 1 plus epsilon. Okay. Then, and suppose that T is not really the sum of the cubic forms. Instead, T is for some error tensor E, okay? And suppose that I only know the following thing about E, that if I look at E as a D by D square matrix, so E is a D by D by D tensor. Let's say I view it as a D by D square matrix by this one of the flattenings that we discussed earlier, and look at its largest singular value. So, because there are many, many matrices you can produce from tensors, people write down these norms because, these are all largest singular values of certain matrices that can be constructed from the tensors. People use notation to describe which matrix we are talking about. And so, here I am talking about the matrix obtained by taking the first mode, as rows, and second and third modes flattened as columns. Okay. So in particular, this norm means take the largest singular value of this matrix. Let's say this is at most, let's say delta. Okay. Then my check will now involve, my check is slightly different. I can't quite check that AIX to, sorry. So remember, I only have input the tensor T. So I'll check that T dot X tensor to the 3 is at least 1 minus delta. Let's call this the new system A, and A derives in degree 2k, just like we proved earlier, in variable X. The inequality sum I AI X to the k is at least 1 minus O of k delta O of k epsilon. Okay, and this is the noise resilient and more general version of the same theorem. And actually the proof is very, very similar. So let me, quickly convince you without really doing the details of this proof that this works, okay? But before even going that, let's make sure that we understand that these checks are legit, We are focusing on soundness, but because we changed our checks, we should also go back and confirm completeness. Why is it true that T dot X tensor to 3, when I initiate X with AIs, are going to satisfy this? Okay, this is going to be really simple. So let's, check that on the side here. So t dot x tensor to the 3 is actually equal to some ai x cubed plus e dot x cubed, right? And now we use the fact that E had this 1,23 norm upper bounded. And we use the fact that spectral upper bounds can be done via sum of squares proofs to conclude that this is at least some ai x cubed minus the largest singular value of E, because x tensor to the 3 is a norm 1 vector. So this is at most, this is at least, what did I assume? Delta. Good, so this is good. But now, I don't have orthonormality. So how do I prove that some ai x cubed is at least large? So I observe that this is equal to, so now, if I plug in x equals ai, let's say a1, then I get a1 cubed. So a1, let's say, you knew that they are unit vectors. Let's say maybe I make an extra assumption. So yeah, unit vectors, but not orthonormal. Then, I have a1 cubed plus some I not equal to 1 ai x cubed minus delta. Good. And now what? So, oh, okay, I see. So now I think I'm going to use the following fact. This is A1. So I'm going to use the following fact. Some AI A1 cubed is at most. So I'm going to use the fact that inner product of AI and A1 can be at most 1 because all of these are norm 1 vectors, is at most AI A1 square. I not equal to 1, I not equal to 1. This equals some I AI transposed. Okay, I think maybe I am in trouble here. Okay, this is going to give me a bad bound.
It says 1, right?
Ah, I see. I guess maybe I should do the, okay, sorry. I guess I should do the following proof. So I use the fact that ai.a1 is at most 1, but I'm summing over everything now. And now, I use the fact that this is the quadratic form of this matrix. Use the fact that the largest eigenvalue of some ai transpose is 1 plus epsilon to conclude that this is at most, a1 square, right? And now, this, look at this particular matrix. The first term of this is, the norm of a1 square, which is 1. So if this upper bound has to hold, it implies that some I not equal to 1 ai a1 square is at most epsilon, right? Because the first term is exactly equal to 1. Still following? Good. So, what have I convinced you of? I've convinced you of this term is at most epsilon in magnitude, right? Anyway, so, this line of reasoning tells you in particular that t dot x tensor to the 3 is at least 1 minus delta minus epsilon. So the completeness, okay, so for completeness, I need to check this instead of, so by completeness, I need to make my real solution satisfy the checks I'm doing. So, I verified them for AI and I could prove it with like epsilon plus delta slack. So that's what I did. Good. So that's the proof of completeness. I guess it wasn't super trivial, but also not super hard. So let's just point out that this is proof of completeness. And let's just say that, if you literally repeat the same kind of proof with, the better upper bound on some AI x squared, and, this upper bound on the error tensor, then in fact, you can actually do it using the same proof. So let me not spend time on that because I do have to get to the rounding. Good. Very good. And so, there's actually a lot to say about tensor decomposition, but I want to only complete the proof of this quasi-polynomial algorithm that we have. So what have we done? Like last time, what we do here. So, last time when we proved, or in the last two times, once we had proven soundness, we computed a pseudo distribution, right? And then, somehow did some simple operation on a pseudo distribution to extract our solutions, right? So now we've got to do that here, right? So let mu be a pseudo distribution, and because you're using some fact which was proven in degree 2k, let's say mu be a pseudo distribution of degree 2k. And because the checks were the script A, let's say that the pseudo distribution mu satisfies the checks in script A. Okay. So what can we immediately conclude? Well, the same thing that we've been doing for the last two lectures, that we can take the pseudo expectation of both sides of the soundness inequality, and it must be satisfied because mu is a pseudo distribution of degree at least 2k. So then so let's combine delta and epsilons because they're all tiny for us into one single delta, and let's call it this. Okay, so I don't have to carry around extra notation. Good. So now what? Now what do? I have to extract AIs, and I only have this information. How can I use it? Well, one thing I can conclude is, therefore, there must exist an I such that the pseudo expectation of AI x to the k is at least 1 minus O of k delta over k. Okay. So let's just assume that k delta is at most half, or this O of k delta is at most half, okay? Because that's all I'll care about here. So this is at least 1 over 2k in that case. Okay, so what have I done? I have concluded, so I know that the sum of the pseudo expectations of this R terms is at least 1 minus O of k delta. And so, one of those R terms must be at least 1 over 1 minus O of k delta over R large. Sorry about that earlier. So, this is at least 1 over 2R. Still following me? Yeah. Now notice that, if this is true, then for actual distributions, if mu was an actual distribution, it means that, there must be non-trivial amount of mass in the distribution on AI. You can't quite make this happen if every, if all notice if all points in support of the distribution mu are such that AI x is at most, let's say 1 minus some parameter beta, then the expectation of AI x to the k would be at most one minus beta to the k, right? And if I choose beta to be, let's say some target delta, and k to be 1 over delta times log r, yeah, then this will violate the inequality that I have to be larger than 1 over 2r, right? So for actual distributions, I hope you're all convinced that the only way this inequality could be true is if mu has some mass, like some point in the support of the distribution mu, is really 1 minus beta correlated with AIs, with one of the AIs, right? And so that's some hope, right? Like I can hope to recover one of these AIs. Still with me? Feel free to ask me questions or stop me if I'm confusing you. So that's maybe some intuition to keep in mind if mu was an actual distribution, but it is not. So we've got to come up with a rounding algorithm. Okay. So let's do that. By the way, yeah, one thing I should notice, right? Like the only thing, if this is the only thing we know about the pseudo distribution, notice that the pseudo distribution, it's like the following are all valid solutions. Take any distribution on A1 through AR, then it's a valid solution, right? Because we know that A1 through AR all satisfy the polynomial checks. And we have no control on the distribution that we're using here. So you could use any arbitrary distribution on A1 through AR, and that's supposed to work, right? In particular, this distribution could really be simply, output A1 100% of the times. This is a valid solution. If this is your solution, then you can't quite extract any information about A2 through AR from it. So in general, the pseudo distribution need not give you all the information about AIs, right? It may just give you information about only one of the AIs. So you have to figure out how to, calculate, you have to figure out how to, estimate all AIs, but I will not get into it today, okay? We'll just focus on the task of recovering one solution because, I have like 10 minutes. Okay, so let's do that, okay? So we'll find at least one maximizer of the polynomial. The iteratively doing this trick requires some work, okay? But it can actually be done. But I would not go into it today. Good. So here's a rounding lemma for you. Let mu be a pseudo distribution on X satisfying. So it's a general lemma actually. Suppose, it's a, so you have a pseudo distribution such that, for some unknown vector A, the pseudo expectation of A dot X to the K is at least e to the minus delta K large. And let's say it satisfies the constraint X squared is at most 1. Okay, just like in our situation. So suppose you have such a pseudo distribution which is which satisfies the constraint that X squared is at most 1, and the pseudo expectation of A dot X to the K is at least e to the minus delta K for some unknown vector A. Okay, then there's a n to the O of K time algorithm that succeeds with probability 2 to the minus K over some polynomial in epsilon. I think this in fact is just epsilon square, that outputs A prime such that A dot A prime is at least e to the minus delta, which is 1 minus delta. So what is this, what is this statement saying? It's saying that, suppose for whatever reason you ended up with a pseudo distribution which satisfies the constraints of, the vector being on the sphere, like, of norm at most 1. And that, it has this kth power of the correlation with some unknown vector, which is like somewhat large. Notice that this e to the minus delta K is basically, expression of the form, 1 over 2 to the r, 1 over 2r that we had before, okay? So think of K as log r over delta. So if I instantiate, our situation with K equals log r over delta, then notice that e to the minus delta K is simply 1 over r. Okay, so I've just parameterized it this way because it's easier to, do this rounding task. Good. So what is it saying? It's saying if you have so this is like 1 over 2r for K log r over delta. It's saying that, if you have this condition, then in fact you can give a algorithm. It's going to be a randomized algorithm. So it's only going to succeed with some fixed probability that depends on this constant K. So notice that for K equals log r over delta, this will succeed with like some inverse polynomial probability in R, which is fine for us. We're already spending, n to the k time. So, this inverse polynomial success is not that bad a thing because we can just repeat the algorithm many, many times. And with that, probability is going to output an A prime, which is, e to the minus delta correlated with A of unit norm. And e to the minus delta is like 1 minus delta. So, you were able to basically you improved this e to the minus delta k to e to the minus delta. So in some sense, you were allowed to like this. You can think of this as, you think of this lemma as saying that you can like somehow, take 1 over kth powers of both sides before taking expectations. Like in some sense, that's the way to think about this lemma, right? Like, let me in fact clarify this comment. Note, suppose you had this inequality. Okay, instead of, so notice that we only have pseudo expectation ax to the k is at least e to the minus delta k, right? But suppose I canceled out k over two things before taking expectations somehow. Okay, you can't quite do this, but this lemma is allowing you to somehow, eventually think of it that way. Okay, so if you had this, then you can round easily. Okay, and let me ask you for suggestions here, because just to see to see what would you do here if you had the second power being large. What's a good rounding to do if you have this inequality? Suggestions? Well, okay, let me help you out, okay? Look at this matrix. Okay? Then you know that the pseudo distribution satisfies the constraint that x squared is at most 1, right? So, which means I can take expectations of both sides, right? What does this mean? It means that sum of xi square is at most 1. Well, notice that the trace of this matrix is simply this. Okay, so you have a matrix whose trace is at most 1, right? So you have a matrix whose trace is at most 1. And it's a positive semi-definite matrix because, pseudo expectation of XX transpose is PSD. So we have a PSD matrix with trace at most 1. And, what does this inequality say? This inequality says that A transpose pseudo expectation XX transposed A is at least 1 minus delta. Okay. What is this saying? It means that it has at least one eigenvector with eigenvalue bigger than 1 minus delta. Still with me? So you have a matrix. Okay. Let's say its eigenvalues are lambda 1 through lambda d. Then sum of the lambda, these are all non-negative. They add up to something at most 1. And you know that lambda 1 is at least 1 minus delta. And you know that the largest eigenvector, has to be somewhat correlated with A, because otherwise this is impossible. Otherwise, you can't quite have 1 minus delta in a product because, notice the second largest eigenvalue can be at most delta. Okay. So let me not even like go into detailed discussion of this, but it should be, intuitively obvious that, from here on, just taking the largest eigenvector of the pseudo expectation of XX transpose should do the job. Right? It should give you some vector which is, 1 minus O of delta correlated with, A. So I'll just say, so top eigenvector of pseudo expectation XX transposed works. Good. So think of this as your goal. Right? We want to get a pseudo distribution which satisfies this inequality, but we don't quite have that. So how should we do that? So again, this is an idea that we have seen before. The idea is to use reweighting. So I hope you remember this idea that came up when we were doing global correlation rounding, where we did a simpler case of reweighting, where we conditioned on a few variables, and then were able to solve this problem of max cut on low rank graphs. At that time, we had defined reweightings of pseudo distributions, right? So if mu is a pseudo distribution and p is a sum of squares polynomial, then the reweighting mu prime is simply, where you replace the probability with respect to mu prime as a weighted. You just like reweight the probability of any atom by px. And actually, this operation has a simple meaning in terms of pseudo expectations. If you remember, the pseudo expectations of any f with respect to mu prime is equal to pseudo expectation f times p over pseudo expectation p. Okay, so hope this is all coming back to you. This is the reweighting business that we studied. And one thing we proved there was that if mu is a degree d pseudo distribution and p is a degree d minus 2 polynomial, then mu prime is a degree 2 pseudo distribution, right? And you can compute expectation with respect to it by this formula. Good. So let's recall that, and let's convince. So let's convince ourselves that in fact. So here is a simple claim that I'll prove. Okay, so let's be a bit more clear. Let mu be a pseudo distribution that satisfies this constraint, and suppose e twiddle mu of ax to the k is at least 1 minus O of k delta. Okay. Or actually, in this world, we have reparameterized it to e to the minus delta k, let's say. Okay. Then there is a k minus 2 degree SoS reweighting of mu such that e twiddle mu ax square is at least e to the minus delta. Okay. Notice that this is not enough, right? The existence of a reweighting is not enough because we are claiming an n to the O of k time algorithm. So I need to be able to find this reweighting efficiently too. But let me convince you of this and then hand wave why I can do it efficiently. Okay, because I have like 1 minute. So in 1 minute, I'm going to prove to you this, simple but cool claim. So consider the following polynomials. Okay, notice that k is even. So all of these are squares. Okay. I don't quite know A, so these polynomials are not known to me. But these polynomials are there somewhere in the universe, and I can reweight my pseudo distribution with each of them, right? So now what happens when I reweight? Actually, let's add 1 to this list. So 1 means that I have not reweighted at all. Okay. Now what happens? So if I reweight and then take expectations of ax square, what happens? Well, the first reweighting gives me this. And then, the last reweighting, maybe I can write one more term. The second reweighting gives me ax to the 4 over ax square. Right, that's what the expectation of ax square becomes after I reweight it by ax square. And the final thing is ax to the k over ax to the k minus 2. Okay, so I have like I have k terms here. Okay, now suppose without reweighting, the expectation of ax square is at most e to the minus delta. Like if this is not true, then I'm already done. So I don't need to do any reweighting. So assume that it's smaller than e to the minus delta, which means I'm not done. Okay. Now look at these numbers. I know that the pseudo expectation of ax to the k is at least is at least e to the minus k delta. Yeah. And I know that the pseudo expectation of ax square is at most e to the minus delta. Okay. So now I have k, or I guess k minus 2 levels of multiplicative jumps here, right? And my expectation is supposed to go from e to the minus delta to e to the minus k delta. Okay, so by pigeonhole principle, there must exist an I such that, you know, this ratio 2i plus 2 over 2i should be at least e to the minus, so the multiplicative is k minus 1. Okay, so it's like, okay, I guess I can just say this at least. Is this convincing? Like, you know, like, so this is like some telescoping product. Okay, maybe be clear about this at least. So, you know, I have ax to the k over ax square is e to the minus k minus 1 delta. Right? This is the inequality I have by my assumptions. And I'm saying this must imply, so I can write this as a telescoping product. And one of the terms in the product, so they're like k minus 1 terms. So one of the terms must be at least e to the minus delta. And so I'm saying that from here I can conclude that there must exist an I such that ax to the I plus 2 over ax to the I is at least e to the minus delta. And so then, you know, my reweighting is simply ax to the I. Okay, good. So that doesn't really solve anything. So I'll just take like 1 extra minute to tell you how the real thing works. Okay. So what does this show? This shows that there is a reweighting that will give me a pseudo distribution where this, you know, expectation of this ax square is large. But I don't quite know A, so I don't quite know how to come up with this reweightings. So what's the idea? Well, the idea is that I'll actually pick just random Gaussians. Okay. And reweight, so, you know, so actual idea, pick random Gaussians. This should remind you of Yanrick in a certain sense. Pick random Gaussians G1 up to k by 2 minus 1. Okay. And, you know, reweight with g1 dot x square, g1 dot x square, g2 x square, and then, you know, finally, so they're like, I'm giving you like a bunch of reweightings to try out. Okay. Now, why would this work at all intuitively? So, you know, you're going to try you're going to try this. You're going to draw many Gaussians. You're going to repeat this. You know, in fact, remember that I only have to show the success of this algorithm for like some 2 to the minus k probability event. Okay. So the idea is that with some 2 to the minus k probability event, this G will correlate with A up to, you know, so because I'm looking at a 2 to the minus k probability event, I can go to square root k standard deviations in the distribution of G dot A. G dot A is a Gaussian with variance 1. So I can get this correlation to be root log k. Okay. So the point is that, you know, if I repeat this experiment enough number of times, and I can in some sense do it 2 to the k times equivalently, then I will get a G which is like non-trivially correlated with A. And the idea of the reweighting algorithm is that, you know, somehow in here, you know, we reweighted with exactly A, but it turns out that if you have sufficiently correlated vectors with A, the same thing still works. Okay. So that's the reason. So, you know, if we knew what reweighting to do, then of course there is no probability statement in the claim, right? Like we just succeed with probability 1. The reason we succeed with like a small probability is because in some sense, you know, we are going to take a bunch of random Gaussians and, you know, we'll only succeed when the Gaussians have non-trivial correlation with this unknown A. Notice that, you know, whether or not you succeeded can be checked very easily, right? Like at the end, you get a vector. So you can check if it has a large value. So that's not hard. And so the only issue is, can you succeed? And, unfortunately, I don't have time to do the calculations. It's not so hard. But, you can, in fact, implement this idealized reweighting in a certain sense by simply, doing it with random Gaussians. Okay, so yeah, let me stop there. And note that, what we've done is in some fairly general situation that applies to actually even overcomplete, order 3 tensors, we've given a quasi-polynomial algorithm. So what have we done? Let's see. Quasi-polynomial algorithm to recover at least one component of an overcomplete third order tensor. Okay. Let me maybe make just a few quick comments, because we saw only one very special case, right? And the overcompleteness, by the way, came only because we allowed this thing to, like, this is the only condition we input on the vectors, right? And so you can check that, even if I have, let's say, for example, random AIs, but many more than the dimension, this inequality is satisfied. Okay. So, and the other thing we did was, like, we gave an algorithm that is resilient to some amount of noise, right? And in particular, the noise was controlled in this 1,23th norm of this error tensor. That's all we did today. It turns out that you can drastically improve all of these results. So I did not argue how much overcompleteness we can handle, but you can actually go to overcompleteness d to the 1.5. So you can have, like, basically d to the 1.5, maybe up to some logarithmic factor loss number of components. You can do this. You can also do this not in quasi-polynomial time, you can do it in polynomial time. Okay. And okay, so I guess I don't have that much time to tell you some super cool stuff, but the idea is that you don't use this particular rounding algorithm. Instead, you use Yenrich's algorithm as a rounding algorithm on pseudo distributions. Okay. And this is like some super powerful tool. It's like, now you're not trying to replicate the guarantees of Yenrich at all. Instead, you're trying to, build on it. And so in some sense, you can, yeah, sorry, I'm going a lot over, but I promise I'll stop this. Okay. So let's say, you have A1 up to AR. Okay. And R is much, much bigger than N. Sorry, D, the dimension. Now, you can't quite apply Yenrich, right? But so here's an observation. If I look at A1 tensor to the 2, AR tensor to the 2, then these are D square dimensional vectors. Okay. So if I view AI tensor to the 2 as vectors, then these are D square dimensional vectors. So, if these, second tensor powers happen to be linearly independent, then I would be able to apply Yenrich's algorithm, right? So in particular, one observation I want to leave you with is, if I was given AI tensor to the 6, I would be able to apply Yenrich's algorithm by just viewing this as AI tensor to 3. And this time I will be able to handle, many more than D components. Of course, the point is that you don't quite have this. You have access to only, third order tensors. So the way sum of squares comes into play is with the kind of proof we did. Remember how we, started with this inequality, and we derived, all sorts of higher moment inequalities. In particular, we derived this inequality. It turns out that from here on, you can view the pseudo distribution that satisfies this inequality. You can view this guy. If you look at the, if you look at the moment tensor of this guy, then you can actually view it with some ideas as simply the 6th powers of the original components. So the new idea that allows all these algorithms to become polynomial is to, you view these derivations that we were doing as ways to compute higher power tensors from lower power tensors. And then the idea is that, if this is really true, then you can apply Yenrik's algorithm to the pseudo distribution and do rounding. Of course, this is way more, requires many more ideas, and I haven't explained that to you. But this is just to show you that, what we did was like, scratching the surface of this, real important problem. We saw like one simple algorithm, which is really useful, but you can go a lot beyond this. Cool. Let me stop there. And yeah, take questions. Any questions?
So do we have anything about higher order tensors?
Yeah, I mean, so I guess I was very, very fast in the end, but, one observation I was mentioning at the end is that, if you had, let's say, sixth order tensors, right?
Yeah.
Then you can just view the sixth order tensor as a third order tensor of AI tensor to the 2, which means that now you can handle D square components just by Yenrik's algorithm.
Yeah.
And like I was mentioning situations where even though you're not given the sixth order tensor, you can kind of pretend that you have it by, by this idea that we will discuss today, that we can, in generic situations, even in overcomplete situations, we can, start from AI x to the cube inequality that we have, given, just from the tensor that we are given input, we can derive this inequality, right? But what was the issue today? Like the reason this inequality was not useful to us is because we didn't know how to round, right?
Yeah.
Even today, we derive this inequality for overcomplete case, but we just didn't know what to do with it. To round, we had to somehow, with the rounding that we discussed today, we have to like somehow go to log R over delta powers, right?
Yeah.
But the new idea of rounding is to, observe, or at least, try to somehow, use this inequality to, make your pseudo distribution give you, or at least pretend to give you an access to the sixth moments of AI, and then apply Yenrik's algorithm to it.
Okay.
So now this is the way, by the way, that this d to the 1.5 algorithm comes about. This polynomial time algorithm to handle, d to the 1.5 over log d vectors, when they are random or smoothed or whatever.